Jeez. Welcome back, everybody. All right, so we do have a couple slides to get through, but it's not really much. It's just a couple things. Yeah. So let's get to it, shall we? Now remember that section. Are you all right?
Yeah, somebody stole my backpack.
So we have, we're talking about how do we calculate limits using a little bit more concrete methods rather than just seeing what it's going to go to by just plugging and chugging in the calculator or looking at the graph. Those I was helping somebody out earlier, and the questions for section 2.2 where it talks about infinite limits, you can use your calculator. Okay, you can use your calculator to visually look at the graph and see, oh, it's going to go up forever, it's going to go down forever. Because you may not see the pattern, like when you're just going and plugging and plugging and plugging and plugging, you're like, it just keeps getting bigger and bigger and bigger and bigger. Do I assume that it's going to infinity? Check it out in your calculator and truly see, okay, yes, this does go up forever, it does go down forever, whatever it may be. Okay? So section 2.3, calculating using limit laws. Now we have this really fancy direct substitution method. When it's applicable, right? Direct substitution is for polynomials or rationals, and we can use the direct substitution method to just plug in and see where the limit would lead to, right? Okay, so I think we had just gotten done with the absolute value questions, right? We had said prove that this limit does not exist, right? That's what we did at the very end of class yesterday, where we said, okay, the left side limit would come out to be -1, the right side limit would come out to be +1, therefore the limit does not exist. If the limit on the left side does not match the limit on the right side, you could say that the full limit does not exist. So let's see whether this piecewise function, whether this limit exists. Okay, whether this limit exists. Now, to see whether a limit exists or not, again, we investigate the left side limit and the right side limit. So let's do that. Here, as x goes to 4. Now, first thing that we can say about this is, let me ask you guys this. Ooh, that's not a pen. What is f of 4? What is f of 4? It is undefined. It doesn't exist, right? F of 4 is undefined right now. Why? Because there is no or equal to over here. So f of 4 is not defined within our piecewise. But again, we are not concerned about what is happening at that point, but rather what is happening around that point. Okay, so let's get into it. Limit as x goes to 4 from the negative, and then we're going to investigate the limit as x goes to 4 from the positive. Because if those two things match, then the limit exists at that place. All right, so the limit as x goes to -4 of f of x. Well, that means that it's going to go from the left side. On the left side of 4, what is this acting like? On the left side of 4, what is this acting like? 8 minus 2x, right? If x is less than 4, so say 3.9, what would this function be? 8 minus 2x. So therefore, this is going to act like the limit as x goes to 4 from the negative of 8 minus 2x. And that's polynomial. We could just do direct substitution. So that means I've got 8 minus 2 times 4, so 0. Right? So the limit from the left side is 0. If I go to calculate the limit from the right side and it's not 0, the limit does not exist. So let's see. Okay, the limit as x goes to 4 from the positive of f of x. Okay, that is like saying the limit as x goes to 4 from positive here, right? Anything above 4, I'm going to say from the positive direction going down toward 4, it's going to act like the square root of x minus 4. Okay. Let's do direct substitution here. We can do direct substitution because this is kind of like a polynomial one. It exists, I guess we could say. It's not undefined. The square root of 4 minus 4 is the square root of 0, which is 0. So we can say that this is true. This is a true statement. The limit as x goes to 4 from the negative is of f of x is equivalent to the limit as x goes to 4 from the positive of f of x, which is also equivalent to 0. So we can say that the full limit as x goes to 4 of f of x is 0. Okay? It's important to make that statement. It's important to make that statement because if we are really, kind of showing that, almost like proving that it exists, then we need to make those statements. We need to make those, like explain it to the reader, right? If we're proving or showing or investigating, we need to make those statements on saying, okay, why am I saying that the limit is 0? Because the limit from the left side equals the limit from the right side, which is all equal to 0. So therefore, the full limit is 0. Explain your work. Okay. All right. Not every day you get to learn about a new function. Today, you guys get to learn about a new function. I don't think you've learned this before. Have you guys ever heard of the greatest integer function? I don't think so. It's this weird function that basically truncates any decimal. Okay, what does it mean by truncate? Truncate means to chop off the decimal, right? To make it short, to make it smaller, right? So if I'm thinking about the greatest integer function of x, and this is what it looks like. Okay, it's like a bracket with an extra line. It's like a bold bracket. So if I take this, 3.5, the greatest integer within 3.5 is what? 3. That's the greatest integer within 3.5. Right? So that's equivalent to 3. So what about 2.1? Well, then that would just be 2, right? What about 2.9? Still 2, right? So basically taking off any decimals and saying the biggest integer within that, okay? It's not rounding up. It's just saying chop it off, truncate it. Take that decimal off. That's the greatest integer within that number, okay? I want to show this. Let me get this out of here. We want to show that the limit as x goes to 3 of this does not exist. I want to show that the limit as x approaches 3 of this greatest integer function does not exist. Now, to show that it does not exist, we want to use the idea of the left side and right side limit. Okay? Yes, sir.
Real quick, on the examples it has listed up there, how is negative 1/2 equal to 1?
What would be the next integer? Like, I'm saying, like, think about it on a number line. You set the negative 1/2, right?
Mm-hmm.
Can I go to 0?
I don't know.
No.
Can you?
No. No, the answer is no.
Okay.
I always have to revert backward on a number line. Because 0 is greater than negative 1/2.
Mm-hmm.
It's not bigger than that. You know what I mean? That'd be like saying running 2.5 up to 3. I can't do that.
Okay.
So negative 1/2 can't go up to 0. It has to revert back down to negative 1.
Okay.
Same thing with like negative 1.5. I can't go up to negative 1. I've got to go back to negative 2.
Okay.
Does that make sense?
Yeah.
It's harder to like mentally think through it.
Yeah. All right. What if it's like 0.2, but it's like positive?
0.
So that goes to 0.
Reverts back to 0. Because 0 is an integer. Always goes to the one before it. This might actually help you. Let me show you what it looks like on a graph. It's actually a step function on a graph. Okay, right here. Let's take a look. Look at that. Here's the greatest integer function. If I have anywhere between negative 1 and 0, it jumps back to negative 1. If it's anywhere between negative 3 and negative 2, the output is negative 3. If it's anywhere between negative 5 and negative 4 for the x value. So like negative 4.5 would be negative 5. It always reverts back to. And notice how I have an open circle on that, right? Because as it gets closer and closer to 2, and then I'm kind of getting into solving the problem a little bit, as it gets closer and closer to 2 from the left side, it's going to still be reverting back to 1. You know what I mean? So let's actually talk about here. Show that the limit does not exist. Well, if I want to show that, I need to show left side limit does not match right side limit. So let's investigate the left side limit. Oh, did I forget my keys down there? All right. So what is the limit from the left side? Well, think about it. At 2.5, what is it going to revert back down to? 2. What about at 2.75? What about at 2.9? 2.99. Okay. So the limit as x approaches 3 from the left side of x is just 2, right? It's always going to be reverting back down to 2. The limit as x goes to 3 from the positive direction of this thing, what would that be? 3, 3.5 goes to 3. 3.4 goes to 3. 3.1 goes to 3. 3.01 goes to 3. It always revert back down to 3. So I just showed right there that the limit does not exist. And how do we prove that? We see, well, we've shown that as x goes to 3 from the negative, it does not equal as x goes to 3 from the positive. Therefore, the full limit of the greatest integer function does not exist. And that's true at every integer. The limit does not exist at any integer, because from the right side, it's not going to match the thing on the left side. Now, in between it will, but. All right, the last topic that we have to talk about is this cool thing called the squeeze theorem. The squeeze theorem. Yeah. The next 2 theorems give 2 additional properties of limits. I wanted to make note of this. I kept this little phrase in here. The proofs can be found in Appendix F. If you want to do any light reading sometime, all the theorems that we have in the book, I love the book because all the theorems that it has, it proves every single theorem within the book. So if you go into the appendices, you can see the proof for every single theorem, which is, it's cool for me. I don't know necessarily cool for you, but that's cool for me. Okay. Because we have equivalence with these limits, we also have inequalities as well. If f of x is less than or equal to g of x, where x is near a, and the limits of f and g are both existent as x approaches a, then we can also say as long as f is always less than g, right? When x is near a, and we can say at a certain value. We can say that at a certain value. So say at x equals 2, the function f is somehow small. The output of f is smaller than g, right? Maybe visually f is lower than g on the graph. If f of x is less than or equal to g of x at a, then the limits as f goes to f and g, as x goes to a at f and g, are less than, it follows that same inequality. Okay? That really doesn't have a lot, that's like, okay, that makes sense. That's like, that's not really groundbreaking here. But this is the cool part about this. You can also, kind of, I don't know how to say this, narrow in. If I say I know there's going to be a function above, and I know there's going to be a function below, and I know the limits of those functions, then I know the middle one has to be in between those as well. Okay? If you know you have 3 functions, f, g, and h, and you know at a certain value, g of x is in the middle, then you also know that the limits as those go in are going to be in between there as well. So therefore, if you can say that the limit of f of x is a certain number, and the limit of h is x is a certain number, L, so maybe I say, well, I know the limit of this thing is 2, and I know the limit of this thing is 2, well, what does that make you assume about the limit of g? It must also have to be 2 as well, right? If you know this is true, where f and h kind of squeeze in the middle function g, then you know the limit as x approaches those numbers on either side. If that's a certain value and g is stuck in the middle, then you don't even have to know anything about what the characteristics of g are. You just have to know that this is in between there. Then you know that g of x has to be equal to that number as well. This is visually what it looks like. My calculus teacher, my Calc 1 teacher, he was from Georgia, not the city, not the state, the country, like European Georgia. So he had this very thick accent, and he always called it by the sandwich theorem. But he always said the sandwich theorem, sandwich like with a V. I always thought that was really kind of cool. But he called it the sandwich theorem, the squeeze theorem, or some people call it the pinching theorem. Basically says that if you know at point A, and look, I think they do this in the diagram to reinforce the fact that I'm not really talking about everywhere on the function. I'm just talking about at A. If at A, f and h, as it gets closer to it, f and h as it approaches A, pinch g in the middle, squeeze g in the middle, then you know the limit as if you know the limit of f and you know the limit of h, and they all converge to be a certain number, then you can assume that g is converging to that certain number as well. Okay. Now, how does this help us? Let's take a look at this problem. I'm going to show that the limit of x goes to 0, limit as x goes to 0, of x squared sine of 1 over x is equal to 0. I'm going to show that it's going to equal 0. Okay. All right, so here's how we're going to do this. We're going to do this by using the squeeze theorem. Let me ask you this. What are the outputs of sine? How does sine vary for the outputs of sine? Like, think about the outputs. Like, think about the unit circle, the y values of the unit circle. What do they range between? 1 and -1, right? I know sine is in between -1 and +1, right? That makes sense to us, right? So no matter what I run through sine, it has to be between -1 and +1. Okay, so let me change the input value then. Is that still true? Yeah. The only thing I have to put a restriction on is that x is not 0. Okay. So can I do any sort of direct substitution here? No, because that's undefined. So what I can do is, now take a look here. This is pretty fancy. I'm going to multiply by x squared through this compound inequality. Because I can do that, because whatever I do to one part, I just have to do to the other part. Okay. So I have negative x squared sine 1 over x, and then positive x squared. Do you see how now I have this chunk in the middle? So I can say now, I can apply the limit to all of these pieces. I can apply the limit as x goes to 0 to all of these pieces. So I can say the limit as x goes to 0 of -x squared is going to be less than or equal to the limit as x goes to 0 of x squared sine 1 over x is less than or equal to the limit as x goes to 0 of x squared. Hi. Okay, hold on, please. We're almost done. But yeah, you're good. Think about the limits on either side. How I get them this good. Think about the limit as negative x squared and the limit as x squared. So you doing all right? What's that? Okay, I'll come to you in a second. So what is the limit as x approaches 0 of negative x squared? Well, can't I just do direct substitution here? Yeah. You're like, if you say so. Can't I do direct substitution here? Yeah. So now I just applied the squeeze theorem. Because look, now I say, if it's in between 0 and 0, what must the limit be equal to? 0. So therefore I can say the limit as x goes to 0 of x squared sine 1 over x must be 0. And it all started with the fact you have to know something about part of the original function. Like we all started with the fact that sine of 1 over x had to range between negative 1 and positive 1. So you can start there and then build off of that to try to make two things on either side to get yourself an inequality. Okay? All right, that's all the notes that we have for today. I'm going to give you the rest of the time to work. See, it is a work day.